Okay, so let's get started with today's lecture. So as you remember, on Monday, we looked at the optimal control problem through a closed loop lens, whereby the object we want to optimize over is a closed loop policy. And we introduced the most fundamental algorithm that we have at our disposal to compute closed loop optimal policies, which is referred to as dynamic programming. We derived the algorithm for a discrete time formulation of the problem. We will actually extend this derivation to continuous time next week, which will lead us to the Hamilton-Jacobi-Bellman equation and the reachability theory. And to do so, we discuss some key structure that the problem, the optimal control problem, as we formulate it, has, that we can leverage to derive dynamic programming equations. And then I presented LQR as one example that allowed me to show you how to apply the dynamic programming recursion. And at the same time, LQR is a problem that is of interest in its own right. Now, in the second piece set, you have a number of opportunities to strengthen your familiarity with dynamic programming and LQR. You'll have one exercise that shows how much computation you save by running dynamic programming as a solution algorithm as opposed to brute force. You'll have one exercise that forces you to implement from scratch an LQR algorithm. I know that you could use an AI agent to do so, but at least for once in your life, try to do it from scratch. And then we'll transition into the material that we're going to discuss today. Specifically, we talked about LQR at the end of the last lecture. Today, rather than introducing new concepts in optimal control, we are actually going to spend the entire lecture on how we can leverage LQR in a variety of different control settings. As I said, LQR is a formulation that is of interest in its own right, widely used in the field of controls and robotics and beyond. So I'm going to dig a little bit deeper on how you can use LQR as part of the control loop. Then next week, we'll generalize the formulation to a stochastic formulation. So we'll assume the dynamics are perturbed by stochastic disturbances. That will lead us to the stochastic version of dynamic programming equations that you might be already familiar with if you're taking a class, decision making under uncertainty. And then next Wednesday, we will cover the continuous time formulation of closed loop optimal control, which will lead us to the extension of the dynamic programming algorithms in continuous time, referred to as the Hamilton-Jacobi-Bellman equation. After that, we'll then move to MPC, just to give you an idea about where we're going. So as I said, today we're going to focus on LQR-style algorithms for optimal control. I will claim that after PID control, LQR is the most widely controlled theoretical algorithm used out there. So it's very important for you to familiarize with the concept. Particularly LQR, as we set it up with the goal of finding a control that drives the state to the origin. That's why it's referred to as a linear quadratic regulator. The goal is to do regulation, to drive the state to the origin. But in general, especially in robotics system, you're not that interested in driving the state to the origin. You want to drive the state toward a desired behavior or a desired trajectory. Can we still do that with LQR? And the answer is yes. And we look at how to use LQR in this setting by looking at LQR as a mechanism to do trajectory tracking, both in a linear setting and a nonlinear setting. Yeah?
You said that this is the most common outside of PID. I was wondering if you could talk maybe for like 30 seconds or so why you would choose this over PID instead of that.
Well, the problem with PID is that you don't really have a notion of an objective function. In LQR, you can more intentionally specify your objectives. There are indirect ways to shape the response of your system with PID controllers. And if you're taking a class like Engineering 105 or 205, you spend quite a bit of time in terms of mapping relationships between phase margin and gauge margin or placement of poles with the rise time and so on, but it's a bit indirect. With LQR, you have a very explicit handle on how to optimize operations. But on top of it, LQR, as we will see today, is very flexible. It can be used not just for stabilization purposes, but also for trajectory tracking purposes, and even as a tool to compute trajectories for optimal control problems.
Would you say that it's been better unless, like, with the ideas like simple to implement?
I think it's very complementary. So typically, PID is used as the last step of your control hierarchy when you really have to manipulate the signals that go into the actuators, literally throttle, steering, opening valves, and such. LQR sits just above PIDs, reasons more about trajectories. So don't view them as in opposition to each other. They're very much complementary. And by the end of this class, we'll have a bit more of a discussion about how you bring all these tools together. Typically, the way that a decision-making logic is architected is that you have typically PID at the end of the day at the lowest level. Then you have some trajectory optimizer, which could be LQR derived, it could be SCP, it could be some other direct method. On top of it, you still have to set objectives. So how do you do that? You can use techniques from decision making. These days, maybe you may want to use more data-driven techniques. You can use large language models, vision language models. And the difference between these layers is essentially the granularity at which the physical knowledge and physical properties of the system are leveraged. Typically, at the level of decision making, you don't really reason about all the nuanced aspect of your dynamics. Like, for example, in your brain, if you want to set the goal of moving to that door, you don't really reason about all the joint displacement in your arms and so on. When you start optimizing for your trajectory, probably you take into account that you are a dynamical system. You need to have some space around you, but still you're not thinking about all the joint level. And then you start going down the control. Does it make sense? Yeah, very good question. All right. So as I said, we're going to look at LQR as an algorithm to derive tracking algorithms, also as a way to devise a new way to compute trajectories for optimal control problems, which sounds a bit weird. So we derive LQR as a solution of an optimal control problem in a very specific setting of linear dynamics and quadratic cost. We'll see how that then can be used as a way to derive a new direct methods for optimal control. It's a bit confusing, but we'll get there. And then we'll look at this algorithm referred to as iterative LQR, quite popular. And then we're going to look at the refinement of iterative LQR, referred to as differential dynamic programming. All of this is rooted in LQR ideas. Now, some of the equations will get a little bit convoluted. For the algebraic purposes, there is nothing particularly complicated here. So I won't be printing all of the update equations for the different matrices and gains and so on. Everything is explicitly provided in the lecture notes that are referenced in this slide and are also referenced in the syllabus. All right, so let's get started. So first of all, a recap about LQR. LQR is a very specific class of an optimal control problem where we don't have constraints on the state, we don't have constraints on the control. The dynamics are linear, SK equal AXK plus BK UK. Note that the dynamics are not necessarily time invariant. Actually, the state matrix A and B can depend on time, as denoted by the subscript K. This will become relevant later. Well, actually, this is a useful property of LQR. And then we assume that we have a quadratic cost. So last time, we looked at the cost until here. So we have a quadratic penalty on the terminal state, plus a running cost that entails a penalty, quadratic penalty on the state, and quadratic penalty on the control. You can slightly generalize this cost, and that changes nothing in terms of our derivations, by also including cross terms, x times u. Why would you like to include this cross term into the cost function? Well, maybe in some situations, the amount to which you want to penalize the control effort might depend on the state you're in. But more mechanically, when we'll be using LQR as a mechanism to devise tracking control algorithms, that will entail performing some linearization. So these additional cross terms will pop up in the cost function. So that's why I want to present the equation in this slightly more generalized form. You can write the cost function here a bit more compactly in matrix form. You have the quadratic term on the state, x transpose qx, quadratic on the controls, u transpose ru, and then you have the cross terms, x hu, u hx, that sum together and give you the equation at the top. So the Bellman equation, as usual, entails minimizing over the controller time k, the current stage cost, plus the cost to go. And we know that in LQR, the cost to go is also quadratic. Specifically, if you do the derivation same as last time, so you start from the boundary condition, which is a quadratic, because of how we set up the terminal cost. And then you go one step later, you set the gradient equal to 0, then you solve for the control, and then you plug that back into the right-hand side of the Bellman equation. You see that the cost is also quadratic. It stays exactly the same. So the addition of the cross term doesn't change anything. So you will find that the optimal control law is still a linear feedback in control, so it's a matrix time state. And the optimal cost is a quadratic in the state. Of course, L and P update equations will change slightly because now we have a cross term. Details of which are in the lecture notes. Not important here to show the exact equations. You can generalize this formulation even further by now introducing not only cross terms, but also linear terms in the state and in the control, and also constant terms. So now you have a cost function that is quadratic in the state, quadratic in the control, linear in the state, linear in the control, plus a constant term. The main reason why we're interested in this kind of generalization is because when we are going to use LQR for tracking purposes, and you perform linearizations, you have these additional terms that pop up. And you can even, for LQR, generalize the dynamics. So looking at a setting whereby xk plus 1 is equal to ak xk plus bk uk plus dk. So now the dynamics are no longer linear. They're referred to as affine because you have a constant forcing term. Think of this term perhaps as disturbance, like, for example, a wind gust that we know will happen at time k. Well, you can do exactly the same derivation we did for standard LQR. So we write down the Bellman equation. We start from the final condition, which is now a quadratic plus linear plus constant terms. We set the gradient equal to 0. We solve for u. Then we plug that back into the right-hand side of the Bellman equation. So what you'll find is that the optimal control policy is a linear feedback term plus a feed-forward term. And the cost function is a quadratic that also has linear terms and constant terms. Yeah?
So the equation when you're using for recapping that we're minimizing was slightly different than the one you talked about in the last lecture.
Yeah, so here the main difference is that I'm adding this cross term. And my main point is that when you do the derivation, the structure of the control law and the optimal cost does not change. You still have linear feedback on the state and quadratic cost. Of course, the gain and the P are going to change slightly.
But also, instead of using Qn, you had the H was there instead. Like this, it was switched. Like your terminal state was using H instead of Q.
Did I change terminology? So you're saying that here I had an H?
And then there was no H though when you were summing it. So it made it seem like it was a completely different, a different matrix that you were multiplying against. Does that?
So here instead of Qn we had what?
Yeah, H.
Okay, but that's fine. That's just a terminology.
Yeah. Okay, but then there wasn't any. Like for example, there's a Q in there, but there is also.
But it was not. This term was.
That was
yeah, 100%. So what I'm saying is that what we had last time was everything up to here.
Yeah. But this Q is from is also like that matrix.
Oh, not to over-index too much on the symbol. This Q is just any
it's not the
matrix that you choose.
Oh, okay.
I couldn't call it like psi. Psi is not great for a matrix. I couldn't call it the W.
Okay, so don't think of it as the same Q.
No.
Okay.
This is just a generic matrix that you choose as a designer. So the idea of LQR is that once you set up a problem, then everything is procedural. You automatically get to the optimal policy and the optimal cost. Now, the burden on you is not to solve the optimal problem, is to set it up. So your burden is to pick R, to pick Q, to pick H, and to pick QN. And this is not always obvious. So this is so-called LQR tuning. It takes quite a bit, actually, to pick these parameters in such a way that you get your desired response. Like, for example, when I was tuning the LQR-based, actually, tracking algorithm for the NVIDIA V program, took about 2-3 months to actually get exactly the parameters that you really want so that you shape the right lateral response and longitudinal response. You want it to be, of course, safe, but also you want it to be very pleasant for the user. So there is a little bit of an art and a little bit of course, you can use simulation to do that and so on and so forth. But the point being, those matrices are just placeholder symbols that you should then select as a designer. Even further, as I said, here we're adding additional terms. So we have the CK, that is something that you will pick as a designer. We have these vectors QK. This is something that you will pick as a designer. Or, as we will see when we do tracking, they are derived from a linearization process. But the main point here is that in this more general setup, the idea, the derivation is exactly the same. Actually, you may want to try to do it by yourself. And what you will get is that the optimal control policy now is a little bit different. So I still entail linear feedback on the state. For example, to your point, this thing here in the previous lecture was called FK. So yeah, sorry for the mix-up. LK XK plus LK. So we have a linear feedback on the state. This is also what we had in the most basic version of LQR. But now we have a feed-forward term, so a constant gain. Actually, there is a very intuitive interpretation of this control law structure. I'll come back to that later. And likewise, now the optimal cost is no longer just x transpose p x, also has linear terms in x and then a constant. All these values, pk, matrix pk, vector pk, constant pk, lk, capital LK, and so on, are all derived through Riccati-like equations, update equations, the specific implementation of which is provided in notes. They're a little bit cumbersome, not super useful to show here. So, bottom line is that LQR can be generalized somewhat to costs where you also have linear terms, constant terms, and cross-penalty terms, and to dynamics that are affine. And the structure of the optimal control policy stays either the same or very similar, modulo the addition of a feed-forward term. And also the structure of the optimal cost stay essentially the same, modulo the addition of some linear terms and constant terms. That's it. Let's get to the interesting part here. So as I said last time, we look at LQR as a mechanism to find controls that allow us to regulate the state of the origin. But in general, we are interested in more general settings whereby we are given some reference trajectory x bar 0, x bar 1, x bar 2, and so on. So we have the reference trajectory x bar 0, x bar 1, x bar n minus 1, actually xn. And then u bar 0, u bar 1, u bar n minus 1. Of course, the control trajectory and the state trajectory are not independent of each other, are linked through the system equations. X is derived through the application of U through the system equations. Where is this reference trajectory coming from? Maybe from one of the rack methods we covered last time. So for example, you run SCP on your general nonlinear optimal control problem. You computed a trajectory in open loop form. And that's a trajectory that you would like to follow. But now the problem is that in real life, you have model mismatches, you have disturbances. So maybe you may not start exactly at x bar 0. Maybe you start here. Maybe there is some disturbance that brings you here. So the question is, how do we find a control U that brings the actual trajectory as close as possible to the desired pre-computed trajectory? That's the problem of the trajectory tracking. Specifically, we want to find a sequence of controls. I put empty bracket here to mean that we want to find a full sequence of controls, U0, U1, U2, all the way to UN-1. Somewhat close, and I will be more specific later, somewhat close to the nominal control sequence, because that's the one that we would like to track. We want to track both the state trajectory and the control trajectory, such that the tracking error defined as the difference between the realized trajectory, the sequence of states that your system actually goes through, and the desired trajectory, so the sequence of states you would have liked to go through, as specified by the pre-computed trajectory, is minimized. Does this sound like a reasonable problem? You're given a nominal trajectory, you want to find a sequence of controls that bring you back to that trajectory. So you want to, so this will be delta x1. For some reason, some disturbance moved you here. Some disturbance that was not modeled when you computed your nominal trajectory. Now you want to get back to your nominal trajectory. So what can you do? Let's first look at the simplest possible case. Not too useful, but it allows to scaffold intuition, whereby the underlying dynamics are linear. So sk plus 1 is equal to ak xk plus bk uk. Okay? So for now, we assume the dynamics are linear, time varying. Now, the reference trajectory or nominal trajectory or desired trajectory, these are all interchangeable terms, has to be a feasible trajectory for your system. So your nominal trajectory also has to satisfy x bar k plus 1 equal ak x bar k plus bk uk. Again, a reference trajectory is a feasible trajectory for your system. For a system. So then, let's just take, instead of reasoning in terms of absolute states or absolute controls, let's reason in terms of deviation variables. So we take the difference between these two equations. What we get is that delta x k plus 1 equal ak delta xk plus bk delta uk, where delta uk are the deviation variables with respect to the control. So they're defined as uk minus u bar k. So then you can see how the problem of tracking actually has been reformulated as an LQR problem with respect to the deviation variables. Why? Because our objective is to bring delta x to 0. Now we have a system that is purely defined in terms of a delta axis and deviation variables. So now, and we want to bring delta x to 0. So now we can see that the problem is to choose the deviation variables delta u such that delta axis goes to 0. If that happens, it means that xk goes to x bar k, and so you have satisfied your objective. Of course, when you run your system, you do not, and this is sometimes a point of confusion, you do not control your system directly with your deviation variables. You have to go back. The control that actually you will inject in your system is equal to UK bar plus delta UK. Because you know that once you use UK as your control, then you go back into the difference equation. You will have that the system in terms of deviation variables is guaranteed to converge to 0. If you pick delta u such that delta x goes to 0. But how do you pick delta u such that delta x goes to 0? You set up an auxiliary LQR problem, whereby you set up a cost function that is quadratic in the deviation variables for the state and quadratic in the deviation variables for the controls. You pick R, Q, and Qn. These are design parameters. And then you just solve LQR with a Riccati equation that will give you the optimal delta UK as LK times delta XK. And then you have found your desired sequence of controls to track your trajectory. Does this make sense? So we started from a tracking problem that at face value didn't have much, didn't look quite different from a regulation problem. But then by reasoning in terms of deviation variables, we were able to reformulate the tracking problem as a regulation problem with respect to deviation variables. We then do control development in the space of deviation variables. And to do that, we formulate an auxiliary LQR problem with cost also defined with respect to deviation variables. And once you have found the optimal control law with respect to the deviation variables, you go back to the original control variables that are the ones that you actually inject into your system. And then you guarantee that with this choice, the deviation variables delta x will go to 0, simply by plugging the definition of the delta u into the equations. Does it make sense? So look at now the structure of your control. So now the structure of your tracking controller has a feed-forward term that is your nominal control. Of course, if your state is exactly equal to your desired state, this term is 0. It means that you are on the nominal trajectory, so you should indeed use the nominal control. So that's a sanity check, that makes sense. But look at the structure. So we have a feed-forward term, which is your nominal control, plus a feedback term that, depending on how far the actual state is from the reference state, it pushes you back into your reference trajectory, mediated through this gain. So it's an open loop term plus a closed loop term. So this structure is actually widely used in controls and robotics. It's referred to as a two-step design. Whereby the idea is that you first use techniques from open loop control to find your nominal trajectory, and then you use techniques for closed loop control to find a controller that locally tries to push you back onto your desired trajectory. Why is this useful? It tries to balance the two competing considerations. On the one hand, you want the computational efficiency of reasoning in terms of open loop trajectories. But at the same time, you want to have the robustness that comes from closed loop control. And here how everything is coming together. You use the techniques from last week to compute this object, and then the techniques from this week to compute a closed-loop controller. Of course, you could solve the optimal control problem in closed loop globally, but that would be extremely time-consuming and perhaps not even useful. Why is not even useful? And then I will get to your questions. Because right now, the formulation that we have looked at is static. So the constraints are given, and so on. But for a robotics application, for example, the environment is dynamic. So I have now the current situation of this room, I plan my path, but maybe one of your colleagues stands up. And now my constraint set changes because I also have a new additional collision constraint that I don't want to bump into the CA, like if she stands up. Which means that in general, you have to reformulate this problem and recompute the solution to this problem periodically in time. So solving for a closed-loop control law that applies globally for all possible state of the world may even be wasteful, because in case you know that you will never reach a state that is very far enough from where you are before you have to recompute anyway your problem. Does it make sense? All right, so question?
I was going to ask, is the gain term L there, is that constant, or does that also change as you deviate?
No, this is a well, it's constant, but the subscript K here means that it depends on the stage. So it's a time varying. Of course, if you change the formulation of the LQR problem, LK would change. But otherwise, no, LK does not change, is not a function of the state. It's a purely constant gain matrix given the current stage.
Just a clarifying question. So we get the bars from, like, let's say we did open loop control or something like that. And then you reformulate it by getting the delta, where I guess I'm a little bit confused where when you got the delta of the UK, now you know UK and you know the bars.
No, you don't know UK. This is just a definition of change of variable. This is, you know it. This is, you do not know it. You just solve for delta U, though. And once you actually reason about delta U and you assign a value to delta U, then you can.
And that's at the time varying.
Yep, that's right. Yep. So this seems reasonable. On the other hand, all of this was derived under the assumption of linear dynamics. A more interesting setting is a setting where you have a nonlinear dynamical system. So how do you do tracking when now the dynamics are nonlinear? Turns out that we use essentially the same techniques we have just discussed. So specifically, let's assume that now our system dynamics are nonlinear. So xk plus 1 is equal to f of xk uk. Let's assume, as before, we're given a reference trajectory, again computed through a direct method, for example, through SCP. Now the question, again, is to find a sequence of controls U that bring your state trajectory and also control trajectory as close as possible to their nominal counterparts. On the other hand, though, now the dynamics are no longer linear. So we have that your system dynamics obey sk plus 1 equal of xk uk, and then you have that your nominal trajectory, which has to be a feasible trajectory, satisfies xk plus 1 equal f of xk uk. Can we still reformulate the tracking problem in the deviation variables? Yes, if we apply the following trick. So sk plus 1 minus x bar k plus 1 is equal to f of x uk minus f of x bar k u bar k. But now, let's do the usual trick. So let's do a Taylor expansion whereby we approximate f around its argument x and u, evaluated at x bar and u bar. So if you do so, then we can write f of xu as f of x bar k, comma u bar k, plus gradient of f with respect to x times xk minus x bar k, plus gradient of f with respect to u multiplied uk minus u bar k. Jacobians, yeah. So let's call these derivatives as ak. Let's call these derivatives as bk. So once we plug this formulation in here, what we get is sk plus 1 minus x bar k. So I'm just substituting in here the linear approximation of fx and u. So what we get, this is equal to f x bar k, comma u bar k, plus a k xk minus x bar k, plus bk uk minus u bar k, minus f of x bar k, u bar k. So these two terms cancel out. We define, as before, the deviation variable as xk minus x bar k. So this is the deviation variable for x of k plus 1. This is the deviation variable for u. This is the deviation variable for x. When you, sorry?
So when you first, like, your Taylor expansion, it only holds, like, somewhat true if they're near each other.
That's right.
But they're not guaranteed to be near each other.
No. Yes. Well, so this is a tracking problem. So typically, you start very close to the initial condition that you used in order to get your nominal trajectory. And the idea of a tracking algorithm is actually to stay close to your tracking, to your nominal trajectory. So in that sense, the problem is such that you want to stay close to the nominal trajectory, which means that the linearization typically is a good approximation because you're close enough. But it's true, there is always the danger that you are deviating a bit too much, in which case the linearization becomes useless. And this algorithm could become erratic. In practice, it works quite well. But yeah, it's a very valid point. But the main point here is that, as you saw, if we just by this approximation that the dynamics can be linearized, we are back to the linear setting whereby the dynamics for our deviation variables are linear, which means that, again, I can set up an auxiliary LQR problems with respect to the delta U and delta X variables, find the optimal delta U, and then backtrack the tracking algorithm, the tracking control signal as U bar K plus delta UK. So once basically you do linearization, you're back again into the setup we had in the previous slide of linear dynamics. Something that I want to note here is that these Jacobians here are evaluated at xk UK. xk UK. You are linearizing essentially around the nominal state you should be at time k, time 1 in this example, which essentially means that these Jacobians are actually time dependent. The dependency stems from the fact that you are linearizing at different stages with respect to different points on the trajectory. Fortunately, LQR works for linear time-varying dynamics. So this is not a problem here. Yeah, absolutely. If you had a feasible trajectory, but in reality, what happens is that you're, again, a robotic system, you're moving around in your environment, and new stuff happens, so you compute a new open loop trajectory. So that's why in some settings you cannot really pre-compute the linearized Jacobians. But otherwise, if actually the environment is static, then absolutely you can do that. You can do that. Yeah, that's a great question. So here, we're assuming that we know not just the trajectory in the state variables, but also in the control variables. So in that case, you have, so first of all, for some of the algorithms that we have used, they give you the full state control pair. In other settings, and that becomes a little bit more problem dependent, if you are given a state trajectory, you can backtrack the controls that give rise to that state through the dynamics, for example, using techniques from differential flatness. So bottom line is either you use an algorithm that gives you the state control pair, or somehow you have to backtrack the controls that give you that state trajectory. Otherwise, you cannot really use this formulation. Okay. So that's actually quite useful. And again, note the very intuitive form of your tracking control sequence. A feed-forward term, this is the nominal control that you would like to use, plus a term delta U that, because of LQR, is given by linear feedback on the state. So it's a closed loop wrapper around your nominal trajectory. Very natural. So you have your nominal trajectory, someone pushes you, and then you have a little bit of a control algorithm brings you back to where you wanted to go. Let's go one step further. Consider now the nonlinear optimal control problem. And interestingly, let's now pose the question. Can we use LQR to compute an optimal open loop trajectory? It's a bit weird because right now we're talking about closed loop control policy. So we are using techniques from closed loop control to compute an optimal open loop trajectory. So we'll see why that is a good idea in a second. But for now, the problem is as follows. We go back to our general nonlinear optimal control formulation. We want to find an optimal state control trajectory for it. Can we use LQR ideas to do so, to derive a new methodology to compute trajectories for nonlinear systems? And the idea here is very similar to what we did for nonlinear tracking, but with a little bit of twist in the interpretation. So specifically, let's assume that now we're given a feasible nominal trajectory. This could be any trajectory as long as it is feasible. Now, the idea is not that we want to find a control that brings you closer to the nominal trajectory, but rather a control that deforms your nominal trajectory into a better trajectory. So we want to get away from the nominal trajectory, hoping to find a trajectory that has a lower cost. So you're given a trajectory here, x bar 0, x bar 1, x bar 2. So before, say that for some reason you ended up at x1, you wanted to compute a control that was bringing you back to the nominal trajectory in terms of the variables delta x. Now, what actually you want to do is to find controls that shift these waypoints away by quantity delta x1, a quantity delta x2, such that now you have a new trajectory with a cost C2 that, when compared to cost C1, is lower. So basically, you want to perturb each waypoint in such a way that you get a new trajectory with lower cost. So then the question is, can we use LQR techniques to select these kind of perturbations in a principled way? Yeah.
So if I guess I'm confused how you get a C2 that's less than C1 if you already had your nominal, and assuming that.
But the nominal is not necessarily optimal. So the nominal trajectory is a feasible trajectory with some cost of C1, but I'm not making any claim of optimality for it. So now I want to get a new feasible trajectory, but hopefully with lower cost.
So previously you mentioned how we used previous methods to find like an optimal trajectory, and then the original idea for LQR, like for tracking.
That's right.
Convert. So what situations would we, in this case, we would just not have done that because we have a feasible nominal trajectory, but we know it's not optimal or something.
Well, so the question is, where is that nominal trajectory is coming from for tracking purposes? It might be coming from SCP, for example. Here, I'm going to derive a new method to come up with a nominal trajectory. And then you will use a QR to track it. So that's a little bit confusing part that you shouldn't be tripped. That's right. So for now, we are shifting gears. We're not talking about tracking. Now we're talking about trajectory optimization. Okay? So the idea here is very similar as before. We want to reason in terms of deviation variables, but now we want to pick these deviation variables not to drive delta x to 0, but to drive delta x in such a way that we get the new waypoints that give us rise to a trajectory with lower cost. So the idea, as before, is to consider a linearization of your dynamics so that you still have linear dynamics with respect to your deviation variables, delta x and delta u. But now, rather than setting up an auxiliary LQR problem where the goal is to drive delta x to 0, you consider a different cost. The dynamics are the same, but the cost is different. Specifically, what you do is you have the cost of your nominal trajectory, C x bar u bar k. This is what, okay. The cumulative cost would then be equal to C1. And then you have the cost of a general state control pair, UK. So then you can write C of xk plus delta xk and C of u. In terms of the deviation variable only, by just using a Taylor expansion up to second order terms. So we are approximating the cost of a trajectory with respect to the nominal trajectory. Let me explain this a bit more. So the dynamics are we already had the dynamics in terms of deviation variables through the linearization of the dynamics F. Now, what I want to do is also to find an approximation for the cost in a way that can be used in an LQR-like setting. Specifically, the cost of C xk uk is equal to C of xk plus delta xk comma UK plus delta UK with bars and bars. Okay, oops. Simply because remember that delta x is equal to x minus x bar, and delta u is equal to UK minus u bar k. So this step should be obvious. now I do the approximation whereby C of x bar plus delta x, u bar plus delta u is equal to C of x bar k, u bar k, plus derivative of C with respect to x times delta x, plus derivative of cos with respect to u times delta u. So here, subscript x means that you are taking the derivative of the cost function with respect to the x variables. Subscript u means that we are taking the derivative of c with respect to the u variables. Double x means that we're taking twice derivatives with respect to the x variables. And xu, it means that we take a cross derivatives first with respect to x and then with respect to u. Here we're just doing a Taylor expansion of the function cxu around x bar, u bar, up to second order. So then the idea is, let's compute the deviation variables delta u in such a way that the pair delta u delta plus the second order terms. In such a way that the pair delta x delta u achieve an approximated cost that is lower than the nominal cost. So going back to this drawing here, essentially we are considering approximation of our cost function that allow us to inform the direction along which we want to deform our trajectory. Does it make sense? Yeah.
You were like regularizing it so that, or regulating it so that the delta becomes zero, right? Like the difference between the
For tracking.
and the...
For tracking.
For tracking, yeah.
Yes.
For this one here, it seems like you're like intentionally making the deviation non-zero. So like,
That's right.
what's the parameter that you like bring to zero?
No, here you don't want to bring the delta x to zero.
Something zero, and then so.
Well, remember that this is no longer the standard LQR. This is the generalized LQR. When you also have constant terms and you have cross terms. So that's why the delta x here are not necessarily going to zero. If it was only this term here and this term here, then yes, the delta x then would be picked to go to zero because, of course, you are penalizing them quadratically. So the minimum would be when delta x is equal to zero, which introduces also another consideration. So before, when we were setting up the LQR, the auxiliary LQR problem for tracking purposes, you as a designer picked the penalty Q and the penalty R. Here, the penalty Q, the penalty R, as well as the other matrices are derived from the approximation. So you say, who cares? But you do care because you want this problem to be well-conditioned. For example, you want to have a Q to be positive definite, which means that you may want to regularize some of these parameters. But we'll look at these tricks and the considerations in a second. Yeah?
So it's the idea that you're using the percentability explanations to like estimate what the new costs are going to be.
That's right.
Perturb the waypoint.
Correct. That's right. Yeah. But you do so in such a way that the new cost is quadratic, so then you can use LQR derivation to very quickly derive the solution for delta U. Yeah.
So the cross term, oh, no, I was going to ask why there wasn't two deltas. There is two deltas in the cross term.
That's right.
Because
so
you
it's one half here, and then there is no two there.
No, I see. Okay.
So then the idea, does this make sense? So now we have a cost that rather than encouraging the delta x to go to zero, encouraging the delta x to be chosen in such a way that you get to trajectory to a lower cost. Delta x equals zero is not necessarily the minimum for this cost. Oh, yeah. Okay. So then what do? You linearize your dynamics, you quadratize your cost, you run LQR with respect to the deviation variables delta U. And then you have you have a sequence of controls, UK plus delta UK, where the delta UKs are the ones that are computed through LQR. So now what you do is you go back into your dynamics, starting from the initial condition, and you propagate your dynamics forward to obtain the new trajectory. That becomes the new feasible trajectory that you use for your subsequent round of optimization. So that's why this algorithm is referred to as iterative LQR. You take a nominal trajectory, linearize your dynamics, quadratize your cost, compute the optimal deviation variables delta U, do that for all the stages, then integrate the dynamics forward to also obtain the sequence of states corresponding to the delta U's that you have just computed. This is a trajectory that, in general, has a lower cost, and use that as a new trajectory around which you want to repeat this business. Now, of course, there are a bunch of approximations that are made here, so I'll discuss later when LQR actually may not work. But in general, is the idea clear? Similar to tracking, but just with the opposite twist. You want to deform your trajectory as opposed to go to your trajectory. Now, of course, to your point, once you have computed through iterations of this algorithm a feasible trajectory that you're happy with, then you might set up an LQR tracking algorithm to robustify it. Yeah.
So it's kind of like gradient descent. Are there like any guarantees for how close you're getting with each step of this LQR?
No, not really, because of the approximations that we're making with respect to the dynamics. Which brings essentially, actually, I'll get back to your question in 2 slides. So here, to iterate, iterative LQR essentially comprises 2 steps, a backward pass and a forward pass. In the backward pass, we compute a locally linear dynamics, locally quadratic cost around the nominal trajectory. We solve the Riccati equation to compute the optimal delta deviation variables delta U. And then in the forward pass, we use the optimal control policy, UK plus delta U, in order to obtain the state sequence. Now, something that people sometimes get wrong is when you do the forward propagation of your dynamics, you don't use your linear approximations. You actually use your true dynamics sk plus 1 equal to f of xk UK. Since you know your dynamics and forward propagated dynamics is easy, there is no reason to use an approximation there. So you forward propagate with the exact dynamics. Oh, I have it here. Propagate full nonlinear dynamics, f, not the linear approximate dynamics. And iterate until convergence. Like, for example, as usual, the cost reduction after a few steps is insignificant, or the differences in, for example, in the state space among trajectories is insignificant, then you stop. Or maybe you have a maximum amount of iterations as a budget. So going back to what you know from last week, of course, there are a lot of commonalities with respect to SCP. It's very similar. So you linearize your dynamics, and you can convexify your cost, but with a few differences. So first of all, in SCP, you are using a convex solver to solve the problem. In LQR, you use the LQR equations that are they are actually analytical. So LQR is easier to implement because you're just implementing Riccati equations and then injects some derivatives. With SCP, it's a bit more complex because you also have to implement a convex programming solver. So this seems to imply that LQR is better than SCP. SCP, though, is a bit more powerful. It's more powerful first because it doesn't require necessarily a quadratic formulation of the cost in your approximations. It could just be a general convex approximation. But most importantly, SCP allows you to reason about control constraints and state constraints, as long as the problem is convex. In LQR, there are no constraints. If you add constraints to your problem formulation, all the results related to the Riccati equation don't hold anymore. So they are similar in spirit. They rely on successive approximations, but they're also a bit different in terms of complexity. SCP is a bit more complex, but it's also a bit more general. It's also a bit more, SCP is also a bit more difficult to implement. You have to think about trust regions that we discussed last week and so on. Now, historically, LQR was one of the most popular algorithms because, super easy to implement, Riccati equations plus some linearizations. These days, convex programming solvers, embedded convex programming solvers have become so powerful that even though you have to solve an online optimization through iterations, is not too bad. So SCP has also become a fairly popular direct optimization algorithm. Yeah.
So you can really only use ILQR if you're not close to the limits on your control or the limits on your state, because otherwise
That's right.
There's no reason that your iterations would go over the boundaries.
Yep, that's right. Yeah. So at LQR, you have to be a bit careful in terms of how you handle constraints. You can handle those constraints a little bit ad hoc. For example, you can add penalties into the cost, but you have to be a bit careful. But you cannot handle the constraints explicitly as constraints. Right. So going back to LQR, I'll be a bit quick here. So there are a number of considerations that one has to consider to make LQR work. First of all, as also your colleague mentioned, you have to make sure that the new state control stay close to the linearization point. Otherwise, all the approximations that we have made may not hold anymore, and actually the trajectory that you compute after one iteration might even have larger cost. Which brings us to the second bullet point. So when we roll out the policy forward in time, sometimes you want to detune the control such that you don't get it too far from the trajectory that was computed at the previous iteration. So you may do a little bit of line search in order to find the feed-forward term that keeps you close to the previous trajectory. We need to decide on termination criterion. We have already discussed about this. This is an iterative algorithm, a local optimization algorithm. There is no guarantee to get to an optimal solution. So a good initialization is critical. These days, a very powerful way of initializing these iterative solvers, SCPs, LQR, is, for example, to use data-driven techniques. So basically, neural networks that have seen gazillions of optimal control problems, you just use the prediction from that neural network as a warm start to start these iterations. So you get the best of both worlds, the generality of data-driven control, but also the assurances of formal optimal control. Cost matrices that may not be positive definite when you do your linearization or quadratization, so you may want to regularize them, for example, by adding a constant plus that entity in order to shift the spectrum. In general, there is a great collection of tips and tricks in the thesis of Yuval Tassa, and I refer you to section 2.2.3 if you had to implement an ILQR and you have a little bit of issues with tuning some of the parameters. Now, as a last topic, and here will be quite quick, I want to talk about differential dynamic programming, which is essentially a slightly more powerful way of implementing ILQR-like ideas. At a high level, what DDP is doing is the following. In ILQR, what we do is to locally approximate the dynamics of your system around the nominal trajectory and locally approximate the cost, again, around the nominal trajectory. But once you do that, then you're left with an LQR-like problem that you solve exactly using the Riccati equations. In differential dynamic programming, what you do is to approximate directly the Bellman equation. Specifically, the idea of differential dynamic programming is as follows. So in LQR, you approximate your problem, and then you run dynamic programming exactly. In DTP, you directly approximate the dynamic programming equation. Specifically, you remember from last time, last time, that the optimal cost at stage k given state x of k is equal to the minimum over uk of c of xk uk plus jk plus 1 of f of xk uk. So this is the Bellman equation, right? So this is equal to the minimum over UK plus delta UK. Remember that the delta U is U minus U bar, where U bar is a nominal control trajectory. C of xk plus delta xk, UK plus delta UK, plus jk plus 1 of f of sk plus delta xk, comma uk plus delta uk. So let's define the right-hand side of the Bellman equation as a general function q of xk plus delta xk. Sorry, this should be a bar, and this should be a bar, and this should be a bar, comma u bar k plus delta uk. So this function q is referred to as the q function and will play a crucial role when we talk about the data-driven control. But for now, we don't care about it. So you see that this function is just a function of x bar plus delta x. And so this entire thing is a complicated function of x bar plus delta x and u bar plus delta u. Remember that in dynamic programming, jk plus 1 has already been computed. So this is a known quantity. F, we know it. So we do know this function. We know how to take derivatives. So the idea of dynamic programming is to locally, quadratically approximate the right-hand side of the Bellman equation. So minimum over u bar, so this is just a constant, right? This is a nominal control. Minimum over u bar plus delta u is equivalent of taking just the minimum over delta u. We're optimizing over the same set of numbers. So if you just then approximate q of x bar plus delta x, u bar plus delta u quadratically, now we're just solving a quadratic problems with respect to the delta u's. X is given, x bar is given, so the only variable is delta u. So how do we solve? We're just left with a problem of computing the optimal delta u that minimizes the quadratic approximation of the q function. But this is super easy to do, right? You just take the derivative equal to 0. Do you see what I'm doing here? So in dynamic programming, we are moving backward in time. So this function is known, this function is known. So everything here is known. X is known because you're fixing it in the dynamic programming recursion. The only thing that you're optimizing over are really these delta u variables. Now, what you do in this dynamic programming is to take this very complicated function and approximate it in Taylor series up to second order by using x bar and u bar as your reference point for your approximations. So that now this optimization problem becomes a much easier problem whereby you want to find the delta u's that optimize a quadratic cost, which is really the quadratic approximation of the q function, which is written here This is for the 10th time in this lecture, a second order approximation of a function. So how do I minimize this quadratic function with respect to u? I take the derivative and set it equal to 0. So the derivative of a q with respect to delta u is, this term is a constant. This term is a constant. Here we have a q uk. This term is a constant. Here we have a quadratic. So here we have a plus q. Remember that the subscript u means that this is Jacobian with respect to u. Q u u comma k of delta u plus. So this is a linear term. So we take the derivative with respect to delta u. So we get plus q xu k times delta x. We set all of this equal to 0. And then we solve for the, which is what we have here. And then we solve for the optimal delta u. And that's basically your new control, uk plus delta uk star. So you plug this delta u back into the back into here. So what you get is a solution for a q in quadratic form, which means that now your optimal cost to go is also a quadratic. And then you go one step backward. So basically what you're doing in dynamic, differential dynamic programming is to approximate the right-hand side of the Bellman equation by quadratizing the q function, solving for the optimal delta u with respect to that quadratized version of the q function, get the optimal delta u, plug it back into the cost function so that you have actually a quadratic cost to go, and then go one step backward. So here I'm writing down all the derivatives of the q function, not too useful to remember. The only thing that I want to highlight here, just to draw a comparison with respect to LQR, is that if you go through all the derivations, you'll see that there are second order derivatives with respect to the dynamics. So essentially, differential dynamic programming is a second order algorithm in the sense that it also uses second order derivatives with respect to the dynamics, while in LQR, you only compute the first order derivatives of your dynamics. So this is a little bit more sophisticated algorithm, but in terms of intuition, is relatively similar. So we cover quite a bit of material here. As I said, next week we're going to cover the topic of stochastic DP. But to recap, so we have looked at how to use LQR in a number of settings that are relevant to optimal control, tracking algorithms, very important. Make sure that you familiarize with that material. We also saw how we can derive direct methods for optimal control by exploiting LQR results that led us to the ILQR trajectory optimization algorithm. And then we saw a different way of doing trajectory optimization that is still inspired by ILQR ideas, but is a bit different in the sense that you directly approximate the right-hand side of the Bellman equation. The results are very similar. You still get controls that are a feed-forward term plus a linear feedback term. But of course, the gains are going to be different here. Bottom line, make sure that you familiarize with LQR and with nonlinear tracking with LQR. All right, so see you on Monday.